Yeah, my name is Dirk Bayer from LMU Munich, and this is a collaboration with Jan Strejček from Masaryk University in Czechia. The title is a case study on verification witness validators. So what is a verification witness? If a static analysis tool tells us that the program is correct, satisfies the specification, then of course we wanted to give reason for it, to justify this answer. And this reason can be dumped to a file, and this file we call verification witness. Similarly, if a static analysis tool tells us that the program contains a bug violating the specification, then we would like the static analysis tool to tell us, what is the path through the program on which we can see that the safety property is violated. So, and validators are tools that see whether the witness actually makes sense and is a correct justification for the computed verification result. So we are in the static analysis symposium. So what is our goal? Our goal is we want to verify the correctness of computer programs, but we have the problem that there are programming bugs. Verifiers are programs, and programs have bugs, and therefore they also have bugs, right? And this leads to wrong results. In addition to that, there are static analysis tools that are designed to use an over-approximation that leads to false alarms by design. And this has damaged the reputation of our community, right? Because people in industry were saying, okay, these tools, they give so many alarms that I cannot manually inspect them all one by one and invest time to see whether they are true bug reports or whether they are due to some over-approximation. But there is a solution to this. And the solution is to use the witness and to validate the witness and give the result to the user only if the witness validator has said, oh yes, the witness, the justification actually makes sense, and I can reproduce the result of the witness. And the state of the art is actually quite good. We have lots of tools for static analysis for verifying software systems. There are, I just counted them over the last 11 years, there were 76 static analysis tools for programs written in C and Java. And there are 10 validators currently, like tools that validate the correctness of the verification witnesses. Okay, so here's the picture of what I mean by software verification with witnesses. So the input to the verifier is the program and the specification. The verifier works on it and spits out not only the result, true or false, but also the justification for it, which is written in a witness file, that contains lots of information that can be used further on. This idea is already 7 years old. It's also the idea is also used in data structure research, where they are called certifications for results. And what can we do with these? We can do witness validation. And witness validation is the process of taking the same verification problem, like consisting of the same program and the same specification, plus the witness as input. And the validator tries to reconstruct the proof of correctness or violation of the specification, and the result is true or false, meaning that the witness is confirmed or the witness is rejected. This gives us actually lots of opportunities. For example, we could use untrusted verifiers. We could use verifiers that guess an invariant, for example. We could use machine learning and all that stuff that gives us imprecise answers, because we don't trust the result anyway. We give it to the validator to be sure that's correct, right? And also validation is easier normally than the full verification. So I said there are 10 validators, but the validators were so far used only to confirm results of verification tools, and nobody had studied how good they are actually in refuting witnesses. And we were studying this, and this is actually the contents of this paper. So we were taking all the violation witness validators that you see here lined up, and we were using witnesses from the data set that was produced in the recent competitions on software verification, and we were looking for wrong witnesses. So we were on this slide, we were looking for witnesses that claim to testify a violation of the property. And then we gave those to, and we knew that those are wrong, right? So the witness testifies that there is a bug, but we know there is no bug. And we gave those witnesses to the validators. And this is, the red numbers are telling us, how many witnesses were confirmed by the validators, although we know these witnesses cannot be correct because we know that the program does not have a bug. As you can see, the numbers are not very high. The results are pretty good. So if you look, for example, at this here, there are 5,000 witnesses and only, below 30 of them are wrong. So that's actually pretty good overall. But still, this is not really what we want. We want these numbers to be much smaller. And therefore, we want to have a periodical validation of such validators. And I will give an idea later how to achieve this. For correctness witnesses, it looks a bit different. So this is the red numbers are the number of invalid correctness witnesses, meaning witnesses that say the program is correct, but we know that the program actually had a bug. And here the picture looks pretty good. This one validator here has no false result, wrong result at all. And Ultimate Automizer has only 3 wrong results. And this tool in the middle, which has a lot of wrong results, this was actually, we investigated and asked the developer, and this was actually due to an overall bug. So this gives us a very important insight. Nobody, no competition or so, has looked at the quality of validators so far. And therefore, this slipped through, right? Nobody noticed that this validator here was incorrectly configured. So what we want to propose is to take refutation of witnesses into account. So the current interpretation of validator output in the competition on software verification is as follows. If for a violation witness, the validator gives as output false, then this means the witness is confirmed there is really a violation that the validator also finds, and the verifier receives 1 point for finding the bug. But if the validator gives back true or unknown, then we just say, okay, we cannot confirm the witness, and the verifier gets 0 points. Similarly, for the correctness witnesses, if the validator gives the output true, meaning there is no bug in the found using the invariance from the witness, then the witness is said to be confirmed, and the verifier receives 2 points in the scoring schema. And if the validator says false or unknown, then the witness is not confirmed, and the verifier gets 0 points. So far, what we want to have is that the validators are also used to refute a witness. And we would like to suggest to use this new interpretation of validator output. So as before, if the validator for violation witnesses tells false as answer, then we want to interpret this as the witness is confirmed as usual. But if the validator says true, then this should mean the witness is really refuted, right? And unknown, of course, means the validator could not make sense of the witness and gives up on it. So the violation witness should be refuted if it represents no executable program path that violates the specification. Similarly, for correctness witnesses, we want to add the interpretation of false here. So if the validator tells us false is answer for a correctness witness, then this means the validator found a bug actually in the program and cannot confirm the witness. And the correctness witness should be refuted if it contains either an invariant that does not hold or the program violates the considered property. So this is what we suggested, and we suggested to the competition to create a track on witness validation, and this starts actually with the currently ongoing edition of the competition. And as a benchmark set, like as the witnesses that we take for witness validation, we take those that are computed during the competition itself. And we know what invalid witnesses are, right? We take all those witnesses for incorrect verification results. So for example, if a verifier reports it has found a bug, but we know that the program is correct, then we can take this witness as a truly wrong witness, right? And can use those. For the valid witnesses, we don't have the ground truth. So if the verifier produces a witness and the witness matches, the verification result, then we are not really 100% sure. Imagine the following situation. You have a program, that program has a bug. There's a program pass through the program that ends in a violation of the property. Now a verifier reports that this program has a bug, but the witness describes a different path. And on this path, there is no bug, right? Then the result is correct, and a violation witness is given, but the violation witness might describe a different situation. Therefore, we use the valid question mark in it, right? So here's the scoring schema that we have proposed, and it was that was accepted by the community in the last community meeting of the competition. So this basically is a decision diagram, like if the witness is invalid and a violation validator tells us that it is true, so it refutes the violation witness because it cannot confirm the bug, then it gets 2 points, right? Because it has really done some important work. But if the validator confirms that there is a bug, although there is no bug, because we know that this is an invalid witness, then it gets minus 16 points, right? Similarly, if we have an invalid correctness witness, so this is a witness that contains wrong invariants, which you cannot use to prove the property, and the validator confirms it and claims that those invariants can be used to prove the program correct, then it gets minus 32 points. But if it rejects the witness and tells us, yes, there is a bug, then it gets 1 point. And for the other side, for the validation with valid results, we only use, the positive output, because we cannot really judge whether the witness is truly valid or not, right? It might be that the validator who would, for example, here refute a witness that we considered valid, whether this is correct or not. So therefore, we put a 0 there. But in the future, maybe when we have truly, when we have maybe a data set of truly correct witnesses, then we could put minus numbers there. And this scoring schema was accepted by the community and is currently currently used in the competition track. So the competition track will have the same deadlines and schedule as the competition itself. The pre-runs of verifiers will produce benchmarks that we can later use for the evaluation of the validators. And we will have one category which includes all of the programs and witnesses that we have in the competition, and the overall score will be computed with the same procedure as in the competition itself. So to conclude, validators are an important part of the verification ecosystem. The verifiers include bugs, but also the validators also contain bugs, and therefore we need to validate them. And we propose a competition track for validators, and the competition community has accepted the proposal. And the SAS reviewers, for those of you who reviewed it, thanks for accepting the paper. And for SVComp 23, this current edition, this means this will be the first evaluation, and from now on going, we will have every year an evaluation of validators. If you would like to read more, the papers and the proceedings, please click on it. I also put the slides in the program if you want to have them. Thank you for your attention.
Thank you, very interesting presentation. So when not all the tools and artifacts agree, how do you know for sure what the ground truth is? What is your procedure there to know if the program is actually correct or not, and which of the witnesses, if the tools disagree, is the right one?
Yes, so the verification problems that we have, they are all stored in a publicly available repository. It's called the SV benchmarks repository, and it contains, I think, 20,000 verification problems. And those are contributed from various sources. And one of the sources is, somebody writes a paper and proves correctness or violation of this program, and then we take this and hope the proof in the paper is correct, right? And so this is one thing. So the design of the verification task is such that we can trust it. And the other source of the truth is that if the verification problems are solved again and again by several different tools, then we have the trust basically by all the community researchers that have created those tools that they are correct and that the expected results are correct. Now, if it happens that somebody so for example, I submit a verifier to the competition, and I get the result back, and I don't agree that the result of my verifier is deemed incorrect, and I get minus 16 or minus 32 points, right? Then I can have a look at my witness that I produced and see why is it considered wrong, can find out what is the reason, and then I can fix the program and submit to the benchmark repository a merge request that contains the fix, and that shows actually why, for example, my error path that I found is really a bug, right? And then the community discusses it and then fixes the program or the specification, right? So either the expected result is changed or the program is fixed. And then so this way, basically, if there is disagreement, this will be resolved.
Thanks, and I guess this also applies to, like, if I have a super witness validator that has a feature that no other validator has, and I claim that it's correct and nobody else can verify it, so then it's also a similar process. Like it uses some very complex reasoning that maybe a human cannot follow, but it may provide witnesses where other tools cannot. So then it's a similar process over time, I guess.
So there are certain subcategories for which there are no witness validators yet, and those are problematic. And of course, there's still a demand of more validators to fill those gaps. And on the other hand, there are also, what was on the other hand, what I wanted to say? So you mentioned the case that, okay, there are verification problems that are so difficult that only one verifier can solve them and no other.
Yes, and a human maybe is not able to follow the code logic anymore.
Yeah, so broadly speaking, we have the competition, the rules of the competition is set up such that a new category can be established only if there are at least 3 tools participating. Exactly in order to avoid this, that there is a category where some expert does something and nobody else can compete or can contribute something. But inside a category where many verification tools participate, there could be one program that is so sophisticated or so that only one machine can solve it and nobody else. And then, yeah, then we would have to trust basically the contributor of the verification task that the expected result is correctly set.
Thanks.
Yeah, Bernard? Mm-hmm.
Hi, very nice talk. I may not understand your technique correctly, and I didn't read your paper yet, but I'm interested, say, if you have a flow insensitive points to analysis and you find that there's a nil pointer issue, can you then really go back into the concrete domain and recover the flow with your validator witness? Mm-hmm. Is this possible in your technique?
Yes, so the static analyzer who uses the flow insensitive analysis somehow has to spit out a witness, right? And if, for example, if there is a branching and the analyzer cannot distinguish between the two branching, then the witness should describe both of the branches, right? Because the verifier does not know which of the branch contains the bug. And then basically this witness that contains all the possible paths that could not be distinguished in the insensitivity are validated by the validator. And if the validator can replay the concrete error paths along those paths that are contained in the witness to reproduce the bug, then this witness is confirmed. So it is not necessary that a violation witness contains only exactly one path. This is the ideal violation witness contains only one path, right, on which the tool crashes, on which the program crashes. But if there are several, so the violation witness can in principle describe several paths, and some of them might be infeasible, some of them might be truly executable. This is not a problem, right? The semantics of the violation witness is it describes a set of paths from which at least one violates the specification. And for actually this violation witness validation business, this maybe helps those tools that are flow insensitive, because those tools tend to produce a high number of false alarms. But by basically having one stage analyze and the second stage validate the witness, by this combination, we can reduce the number of false alarms, right? Which is a nice feature, I think. Are there other questions? Julian?
Who verifies a validator? Is there an infinite tower of verification, or do you have a flat structure in mind where you say, oh, the validator actually runs like a concrete execution, and then therefore there is no such infinite tower of validators?
So the question was, who verifies the validators? How to ensure that the validators are correct? It's a question that I cannot answer, right? Because basically the answer is nobody verifies the validators. So what we can do is we need as many as possible in order to compare them, in order to validate them, in order to have yearly evaluations to improve their quality. But there are certain things that create certain levels of trust that are interesting. One thing is for violation witnesses. We can take a violation witness and basically analyze it and replay the error path and generate a test vector for it. And then if we take this, the program, compile it with the test harness and execute it, and if this crashes, then we are pretty sure that this was really a bug, right? And then the developer can step through with a debugger and see that the crash really happens and under which conditions. So this is for the violation part. For the correctness part, what I have in mind here as the ultimate goal is to, so there are ideas around in the community. It's not my own ideas, but so basically verification conditions. So suppose you have a simple program with one simple loop, right? So you need to verify that the beginning of the program until the loop head, that this implies the invariant, that if you assume the invariant and execute the loop once, the invariant is implied again. And then if you exit the loop, assume the invariant, and you go to the assert that you want to prove, then this assert must be implied, right? So these are what we call verification conditions. Now, what we can do is we can basically split the program into pieces and write out straight line programs for each of these verification conditions. And all the mistakes that we make by transforming C programs into verification conditions would be ruled out if we stick with the C code. And then we can have very powerful, so for example, there are interactive verification tools that are not scaling to the sizes of programs that we use in the competition, for example, but that are very expressive and that are based on heavy machinery like Coq and Isabel and so on. And if we basically tell them to prove a straight line program where there is no interaction necessary by a human, right? Then we can be sure that this, that basically if all the programs that I need to prove all my verification conditions are all holding, then I know the verification result is certified by this. So this is what we have in mind, but such a tool does not yet exist. We try to construct it.
Sorry, I'm just curious. So what do correctness validators do today if they don't do that?
The validators, so the task of the validator is use the same verification problem, and in addition, the information from the witness and prove the same, try to re-establish the proof. It doesn't need to be the same proof, but it needs to be a proof for the same problem. And the techniques that the tools use are varying. So there are unbounded tools like, for example, CPA checker and Ultimate Automizer. There are bounded tools that can basically confirm only violation witnesses which have a bounded length. And we have testing-based tools. We have tools that try to come up with a test case to replay the violation and then run the test and see the program crashing. So far, none of the tools are involving Coq or Isabel or this kind of serial improvers. Most of them use SMT solvers, but even if the SMT solvers are 100% correct, but we know by their competitions that there are also problems, then we would still have the question, is the encoding to the SMT formula correct? Like what what Isabel was just talking about.
Oh, I'll ask real quick before lunch. Can you say a bit more about the bugs you found and whether they were sort of correlated across validators? Like, did all the validators get the semantics of this wrong, or was it more like each one had its own like independent bugs?
Can you repeat, please?
The bugs you found in the validators, did like all the validators make sort of the same mistakes? They got the same instances incorrect?
Okay. So yeah, so I think it is very important for the validators to avoid technology bias. So we try to have validators that are based on completely different technologies. So we have, for example, if I want to verify, if I want to validate a witness that was produced with CPA checker, then for me it does not really make much sense to validate this witness with CPA checker's validator, because it is based on the same technology. And if the C program is wrongly encoded in the SMT formula, then we do the same mistake again and confirm. But we have a validator that is based on CPA checker. We have a validator that is based on ultimate automizer. Okay, they are both based on predicates, but they use different SMT servers, they use different encodings, they use different abstraction techniques. Then we use two tools that try to produce tests and run tests, so dynamically executing tests. And let me just remind myself what the tools are. So this CPA checker is based on predicate abstraction and K-induction. CPA witness to test is trying to convert the witness into a test vector and run it. C prover witness to test also, but this one is based on the CPA checker framework, and the other one is based on the CBMC, like they call this framework C prover. So this is based on completely different frameworks. D'Artagnan is a tool for concurrent programs, to verify concurrent programs. MetaVal is a tool that is built on other verification tools. So it's reducing the validation tool it's reducing the validation problem to a verification problem. And Nitwit is an interpreter. So it basically goes through the C program and interprets the values along the path and try to establish the same, that the bug is there. Symbiotic Witch is based on heavy slicing, program transformation, and symbolic execution. And Ultimate Automizer is based on trace abstraction. So it's using interpolation, predicates, and so on. So you see there is pretty a wide variety of technologies. And this way we hope, right, that we don't have the same mistake over and over again. Does this address the question?
Yeah, I think so. Thanks.
Okay, thanks. Mm-hmm.
And that concludes the session. Thanks, everybody. We will resume at 1:30.